Hey everyone, so this is going to be the last video for chapter 7. This is section 7.9 to 7.10. The last two sections of chapter 7 on thermochem. We're going to be talking about basically another way to calculate delta H, the change of enthalpy. So let's go ahead and dive into that right now. Okay, so previously, what did we do for delta H of the reaction? So for delta H, there were two ways that we calculated it. We calculated it through calorimetry, and we calculated it through Hess's law. So in the previous videos, how did we calculate delta H with calorimetry? We used the coffee cup calorimetry, right? Remember, delta H is measuring heat at constant pressure. So you would use a coffee cup calorimeter to do that, and if you know your specific heat of the solution, that is having a reaction, that you're having a reaction in, usually it's that of water. The mass of your solution and the change in temperature of the solution, you can calculate delta H for that reaction, and really just using Q equals mc delta T. For Hess's law, what did we do with Hess's law? The last video, we basically took a bunch of chemical equations that were part of a series of steps that we can then add up to get to an overall equation, right? And remember how we manipulated those equations? We either had to flip them or multiply them by a certain factor, cancel, the stuff from the reactants and the products, whatever was identical on each side. We were able to cancel them out. We were able to add all of those up and then eventually match the overall equation. And then when we matched the overall equation, we took the sum of all the delta H's of every step in that process to get the delta H of the reaction, right? So that's just a little bit of a recap for how we were able to calculate delta H so far. We now turn to a third way to determine delta H, okay? And this is from a tabulated standard enthalpies of formation table, okay? So basically, we're going to get numbers from a table that describe the delta H of particular species, whether they're reactants or products. We're going to look at certain cases, and we're going to be able to calculate delta H in that way. We're going to dive more into what I just said in a little bit, but realize that the delta H is just the change in enthalpy, right? So enthalpy without the delta sign is just a relative quantity, right? It's defined relative to some standard. Remember how we were talking about state functions, and I compared the state functions to like climbing a mountain? And remember what I said, the state function, whenever you have a state function, you don't care about the path of how you got from point A to point B, right? Like if you're climbing a mountain, let's say you start at point A, 3,000 feet, and then you climb to 10,000 feet, right, up a mountain. So point A is 3,000 feet, point B is 10,000. And we know that a state function just says the initial and final states, right? 3,000 feet, 10,000 feet as your initial and final. We don't talk about the path to how we got from 3,000 feet to 10,000 feet. That's why we were able to find certain things as state functions, and delta H is a state function. But realize that even though delta H is a state function, when I say defined relative to some standard, what I really mean is, imagine you're at a particular altitude, right? But the standard altitude is just sea level, right? Because we know that everything is relative to sea level, right? If we're talking about our mountain climbing analogy, the relative point is sea level. And we can go above or below sea level, right? So that's what we mean by delta H is a relative quantity defined relative to some standard. So there has to be a standard for a certain quantity, And if we're talking about our mountain climbing analogy and we set the standard to sea level, then the delta H of a particular uh, chemical also has to have some sort of standard, like a sea level situation, right? And we can calculate the delta H at a standard state, right? So there's three parts to this. There's the standard state, there's the standard enthalpy change, and the standard enthalpy of formation. We're going to talk about each of three of these definitions in depth in just a second. So what is a standard state? A standard state could really just be described as, like I said, a relative state of your particular reactants or products, whatever species exists in a chemical reaction, can have a standard state. If your chemical is in the gaseous form for a gas, the standard state for a gas is the pure gas at a pressure of 1 atm. So that's considered your standard state when you're at 1 atm for a gas. If you're dealing with a liquid or a solid, your standard state is at a pressure of 1 atmosphere and a temperature of 25 degrees Celsius. For a substance in a solution, the standard state is typically at a concentration of 1 molar. Okay? So that's what standard states are. That's how we define them for anything in a chemical reaction. Now, when we're talking about standard enthalpy change, the standard part is this little knot, this little degree sign, right? So delta H is change in enthalpy, but if you're talking about a standard enthalpy change, the standard enthalpy change is the change in enthalpy for a process, for a chemical process, when all the reactants and products are in their standard states. So all the reactants and products have to be in their standard states for you to calculate a standard enthalpy change. Right? That makes sense. If everything's relative to a standard, you're calculating based on that standard, and you can get a delta H standard for that. Okay? All right, so there's also standard enthalpy of formation. So what does that mean? Well, if you have a pure compound, the change in enthalpy when 1 mole of the compound forms from its constituent elements in their standard states is the standard enthalpy of formation. Okay? So what's an example of that? Well, let's say I'm making water, H2O, right? What would be the standard enthalpy of formation of that water? Well, if you take the standard state of hydrogen and the standard state of oxygen, right, the constituent elements that make up water, the compound water, you can then describe the change in enthalpy of 1 mole of water from its constituent elements, right, in their standard state. So imagine you have hydrogen in its standard state and oxygen in its standard state to make water, right, 1 mole of water. So that's what that would mean, is basically the enthalpy change associated with the formation of a pure compound. For a pure element in its standard state, the delta H of formation is just 0. I mean, that makes sense. If you have a pure element, you know, we're not creating or forming an element, right? Elements exist the way that they do, right? They exist naturally on this earth. There's no delta H of formation of an element because that element already exists, and we're not creating any elements here or anything like that, right? So it only makes sense that delta H of formation equal to 0. And here's a table of all the standard enthalpies of formation. So you'll notice that all of the pure elements are 0, right? Br2, Cl2, right? These are all part of Brinkelhoff. F2, right? 0. H2 gas, 0. Sulfur, 0. Nitrogen, 0. All these other compounds, though, notice a lot of them are negative. Why are a lot of them negative? Well, remember, a negative delta H means that the process is exothermic. And it makes sense that when you're forming a compound, you're releasing energy, right? Usually when compounds form, if you're trying to get the delta H of formation of a compound, you do the delta H of the products minus delta H of reactants, it's going to end up becoming negative usually when you're forming a product. Not every single case, but a lot of cases that ends up happening. And we're going to look at some examples. Okay, so here's a practice question. It says write equations for the formation of magnesium carbonate and C6H12O6, which I think is glucose. And it says write equations for the formation of each of these from their respective elements in their standard states. Okay, so how do we go about solving this particular problem? Really, there's nothing crazy about it. We just need to look at, for example, magnesium carbonate. So how do we make magnesium carbonate? Well, we need all of the elements that make up magnesium carbonate, right? We need magnesium. We also need carbon. And if you look at the table, carbon in its elemental form is going to exist as the graphite version, and we can double check that. You guys see carbon solid. Graphite has a standard enthalpy of 0. Okay, so we're going to use that. Magnesium isn't on here, but that's obvious that that's just an element that's not part of Brinkelhoff, and it's in its standard state. We also need oxygen, and oxygen is in its standard state. It's just O2 gas, right? We could check that. I could double check that. Oxygen is over here. O2 gas is 0. And now this is all going to make magnesium carbonate. So what did we just do? We just took all of the elements of the compound and we wrote it out on the left side and their reactants to then make magnesium carbonate. That's really all there is to it. There is one other thing we need to do. We need to balance this equation because right now it's not balanced, right? We have 3 oxygens on the right and only 2 on the left. We can easily fix that issue and put a coefficient of 3/2 in front of the oxygen to balance out the oxygen. You might be wondering, oh, well, now do we multiply this entire equation by 2 to get rid of the denominator? We don't have to do that, right? We don't have to do that. So we're pretty much done here, right? This is the answer for part A. For part B, though, what do we got? C6H12O6. So we do need carbon. So that's going to come from graphite. Plus, we need hydrogen. H2 gas, that's part of Brinkelhoff, right? H doesn't exist just like H like that. It needs to be H2. And then oxygen is also diatomic. And this is going to make C6H12O6. Right, pretty easy. We do need to balance this equation though. So we need 6 carbons on the left. We need 12 hydrogens on the left. We have 2. Let's put a 6 there. And then we need a 3 in front of the O2. And now we're balanced. So all we just did is show the formation, equations for the formation of these compounds. And you can look this up on a table, but you can find the delta H of formation of each of these constituent elements and compounds in their standard states and be able to get a delta H formation of this compound. It should be in a table somewhere, right? Not that you would be asked to look that up. It would probably be given to you, but you can look this up if you want. This also has its own delta H of formation. Okay? So here's a practice question for you as well. Try to write these out, right, in a similar way I just did. And get some practice on writing out the equations for the formation of a compound. Okay, so now we're going to talk about calculating the delta H, the standard delta H, the standard enthalpy change for a reaction. So remember that the delta H of formation corresponds to the formation of a compound from its constituent elements, right? We just did that. We named the elements that make up a compound, and we got the delta H of the formation, right, for that compound. Realize that the negative, though, the negative of the standard enthalpy of formation corresponds to the decomposition of a compound into its constituent elements. So what does that mean? If I'm going to go the other way, if I'm going to go from a compound, right? Let me go back to my pen. If we're going to go from a compound to its constituent elements, we're basically going to decompose a compound into constituent elements. It's basically the reverse process of forming it, right? So the opposite of formation of something is decomposing that thing. And if that's the case, if we're going the other way, remember how we talked about this with Hess's law, that, if we flip an equation, we're going to have to flip the sign of the delta H, right? So this is kind of like flipping an equation, and we're flipping the sign of delta H formation, now becomes negative. Okay, so we've seen something like this before when we were applying Hess's law, but this is just in terms of the delta H of formation. So we can use those two concepts that we just talked about, right? Going from an element to the compound, and then, forming a compound from an element, and then decomposing a compound to its constituent elements. We can use those concepts to calculate the enthalpy change for a reaction. And we're going to use two steps. The first step is we decompose the reactants into their constituent elements. So the first step is decompose your reactants to their elements in their standard states, right? Which just means this knot. Okay? That little degree sign just means standard state. In the second step, we're now going to form the products from the constituent elements in their standard states. So this is step one right here. This is step two. All right, step one, step two. So step one, reactants, decompose them to their elements, and then take those elements and then use them to make the products. Okay? And realize that when we're decomposing in the first step, it has to be the negative delta H of formation. And if we're going from elements to products, that's positive. Now, what's this little Greek letter there here, that sign? That basically is a summation sign. So imagine you're dealing with more than one reactant, basically. Imagine you have 3 reactants. Well, you would take the sum of the decomposition of those 3 reactants, right? That's what that basically means. Right now, it looks like we're just having one reactant and it's going into its elements. What if we have more than one reactant, right? You need to take the sum. And we're going to do some practice problems where we're going to see what that looks like. Okay, here's a situation where I have a standard enthalpy change for a reaction. So here's my reaction. I'm taking methane, CH4. Point my laser. We got CH4 plus oxygen gas makes CO2 and water. Okay, and the question is, what is the standard enthalpy change for this reaction? Well, the first step we need to do is what? We need to decompose a compound into its constituent elements. Right now, oxygen doesn't need to be decomposed because that's an element. We can't decompose an element anymore. But CH4, we can decompose that into its constituent elements, right? Carbon and hydrogen. Like I said, we can't decompose oxygen because it's only oxygen. But we can break this down. Now, you can look this up in your table. The formation of CH4 has to come from carbon and hydrogen, and you can get this number from a table. So this number, I'm going to write this down. This number comes from a table. Now realize this is for the formation of CH4. But we need something to describe the decomposition of CH4. Well, remember, we just flip it, right? So if this is describing the formation of CH4, this is describing the decomposition. So decomposing CH4 into its constituent elements. And notice what happened. The sign changed from negative to positive, just like we talked about. So bottom line is, right now, we did the first step. We've decomposed the compound from its constituent elements. And if you look at this graph, what's happening is, here's where we are right now. So we decompose CH4 into carbon and hydrogen, and we still have our oxygen here. Okay? What's the next step we need to do? The next step we need to do is now use these products and talk about the formation of these products. So we need to do them individually, right? So let's start with CO2. Let's start with CO2. So CO2 is going to be 2A, and here it is. So to make CO2, we need carbon and oxygen to make CO2. And you get this number from a table. Okay, so that's the formation, the enthalpy of formation for CO2. Now you need the enthalpy of formation for water. And there it is. Now, why is it that when we describe the formation of water, which is just coming from hydrogen and oxygen, when we balance the equation, we get half O2, and that's fine. But we're multiplying this entire thing by 2. And why are we doing that? Because there's a coefficient of 2 in front of the H2O. So to get 2 H2Os, if we want to make 2 of them, we have to multiply the equation for the formation of 1 mole of H2O to get 2. So 2 times this means we have to multiply the delta H formation of water by 2 as well. If we're going to multiply the equation by 2, we're going to multiply the equation by 2, we have to multiply the standard enthalpy of formation of water by 2. And you get this number for the formation of water from a table as well. This would be given to you. Okay. And check that out. Relative to our enthalpy graph here, notice our first step was to decompose the methane. So that took some energy. But then notice that the delta H formations of your carbon dioxide and water are negative. So you're releasing energy by forming CO2 and water. And now you can get the delta H of the reaction total. Okay? And there it is. You just add these up, right? Right now, we can look at this. What can we cancel? We can cancel. This is just like Hess's law, right? This is basically Hess's law, where we're adding all of these up. We notice that the carbon cancels, right? Because it's on the products and reactants. What else cancels? Let's see. The H2 cancels, right? What else cancels? I think that's pretty much it. So let's write out what we have. We have CH4 gas plus 2 oxygens. And why do we have 2? Because we have 1 over here and 1 over here. This is going to make CO2 gas, which is left over here, and 2 waters. And that matches our original equation, doesn't it? Let's take a look. Yep, CH4 plus 2 oxygens makes CO2 and 2 waters. Yep, that matches. And if that matches, now we can take all of these delta H's and just add them up. Add them up. Just like we did for Hess's law, right, in the last video. Now, what do we get? We get negative 802.5, right, when you add these up. That's pretty much it. Now, there is a simpler way to do this because this looked kind of annoying, right? We had to basically write out the formation, decomposition, and do all of Hess's law. There's actually an easier way to do this. We can streamline and generalize this process as follows. If you want to calculate the standard enthalpy change for a reaction, delta H reaction, you subtract the sum of the enthalpies of formation of the reactants multiplied by their coefficients, their stoichiometric coefficients, from the sum of the enthalpies of formation of the products multiplied by their stoichiometric coefficients, okay? So you're basically just using this equation, products minus reactants, to get the delta H of the reaction. Really, really, really simple, not complicated at all. Let's do a practice problem related to this so you can actually use this equation. So check this out. This question is a classic ACS style question. They say use the standard enthalpies of formation to determine the standard enthalpy of the reaction, right? And they give you the reaction, and they also give you the numbers that you need, okay? So they basically, like a lot of ACS questions, they'll give you like a little mini table of the values that you need. You may not need all of them. You might only need some of them, right? But in this case, let's see which ones we end up using. So let's remind ourselves that, let me get the pen back here. Where's my pen? Okay. Delta H of the reaction is going to be equal to the sum of the stoichiometric amounts of the product, delta H formation of our product, minus the sum the reactants. All right, so this is the equation from the previous slide. How do we use this equation? Well, let's just look at the products for now. This is really, really simple. I just want you to watch what I'm doing here. What are our products? We have NO and H2O, right? And where are NO and H2O in our table? They're right over here, okay? And notice that we have the enthalpies of formation for each of them. Also notice that we have 4 NOs and 6 H2Os. So the first thing I'm going to do is I'm going to just look at NO. So we're going to take 4 times the delta H standard enthalpy of formation of NO gas, right? Plus 6 delta H formations of water That's all my products, right? This is going to be minus, which is this minus, the sum of the reactants, which is just NH3 and oxygen. Notice we have 4 of those and 5 of those. So I'm going to write bracket 4 delta H formation of NH3 plus 5 of the oxygens. Hopefully you're with me so far. Now what are we going to do? We're going to do 4 times whatever that number is. So for the standard enthalpy of formation of NO is positive 91.3. I'm just going to do times 91.3, positive 91.3 kilojoules, right? Notice this is in kilojoules per mole, plus 6 times the enthalpy, standard enthalpy of formation of water, which is negative 241.8 kilojoules. And you guys can get the idea here, right? For NH3, it's going to be negative 45.9 kilojoules plus 5 times oxygen. Realize oxygen is 0. That makes sense. The standard enthalpy of formation of any element is going to be 0. Okay, now you can get the answer for one of them. It's going to be negative 1085.6 kilojoules for that side, minus, this is going to be negative 183.6 kilojoules. And then you could do this on your calculator. You should get negative 902.0 kilojoules is the delta H for your reaction. Really simple, right? Like, this is really not that complicated. Notice the first time we did this, where we were, you know, kind of manipulating the equations using Hess's law, we still got to the same answer. Like, we still got to the right answer using Hess's law, but realize there's an easier way to do this other than using Hess's law, right? It's just literally using this equation. But you would need this table, though. You would need this. Need this. To use this, right? You can't use this equation if you don't have the table of values, right? How else would you use it? So this is honestly the easiest way to calculate delta H of the reaction. Hess's law is probably the most annoying one, right? Because you have to cross things out, you got to flip equations, you got to multiply them by a factor, you got to do all this shit, right? But at the end of the day, it still accomplishes the same goal, right? Which is you're calculating delta H of a reaction. So let's just kind of summarize how we calculated delta H of a reaction. We can do it using calorimetry, right? The coffee cup calorimetry. We can use Hess's law if we're given all the steps in, you know, for the overall reaction. Or we could do it this way, right? Using this equation. Using the standard enthalpies of formation. Okay, let's do one more practice problem before we're done. So let's just read the problem. It says, a city of 100,000 people uses approximately 1.0 times 10 to the 11 kilojoules of energy per day. Suppose all of that energy comes from the combustion of liquid octane to form gaseous water and gaseous carbon dioxide. Okay, so we're burning some fuel. It's a lot of fuel. Use standard enthalpies of formation to calculate delta H of the reaction for the combustion of octane, and then determine the number of kilograms of octane necessary to provide this amount of energy. Okay, so I think the first thing we could do is just calculate delta H for the reaction, right? And look at this. We have a table. We have a table that we can use. And, you know, if we have a table, we know we can calculate the delta H of a reaction in its standard state by taking the sum of, you know, the products minus the sum of the delta H naught formation of the reactants. Okay, so let's see what we got. In our products, we have 8 carbon dioxides and we got 9 waters. So that's going to be 8 times the delta H naught formation of CO2 plus 9 delta H formation of water. So that's all the products minus, now we got 1 octane and 25 over 2 oxygens. So 1 times delta H formation of octane plus 25 over 2 delta H formation of oxygen, which, by the way, we already know is 0, but we're writing that out. All right, so this is going to be 8 times CO2. That's negative 393.5 based on our table. This is going to be plus 9 times water is negative 241.8 kilojoules. This is all minus 1 times negative 250.1 kilojoules plus 25 over 2 times 0, right? Okay. We do all of this math, we should get negative 5,074.1 kilojoules. This is delta H of the reaction. Okay, when you do that math, that's what you should get. But we're not done with this problem because they asked you to determine the number of kilograms of octane necessary to provide this amount of energy. And what amount of energy? 1.0 times 10 to the 11. So if I have 1.0 times 10 to the 11 kilojoules of octane that was burned, well, I know that for every 1 mole of octane, C8H18, 1 mole, I use this amount of energy. Negative 5,074.1 kilojoules. But they wanted kilograms of octane. Right now we have moles of octane. How do we go from moles to kilograms? Well, why don't we go from moles to grams using the molar mass of octane? Molar mass of octane, by the way, you can calculate yourselves, but it's 114.22. And then you can go from grams to kilograms by saying for every 1,000 grams, I have a kilogram. Do a little stoichiometry. Notice the kilojoule cancels. The moles of C8H18 cancel. Grams cancel. You're left with kilograms. And when you do this on your calculator, you should get 2.3 times 10 to the 6 kilograms of C8H18, which is octane. Okay? All right, so like I said, this is pretty easy, right? As long as you get this table, guys, it's a straight shot from there, right? You can calculate delta H of your reaction, and then, you know, whatever else the problem wants, you can use some stoichiometry based on the balanced chemical equation to get any other piece of information that the problem may want. Okay? All right. That pretty much concludes all of Objective 12. Thank you for watching. And if you have any questions, feel free to ask me either in my office hours or through email or any way to find me. Okay?